Let's move on to lesson 5A. Continuing with similar figures, we're going to talk about the lengths, areas, and their volumes. Theorem 11.5.1a. The altitudes extending to corresponding sides of similar triangles are in the same ratio as the lengths of the corresponding sides. So what we're now getting down to is the fact that by definition, the sides of similar triangles are proportional. All we need to know is that the similar triangles are proportional, and then we can use those same proportions to solve all the other pieces of the triangles. So the theorems, the next few theorems that we're going to learn, show that the same similarity ratio applies to the lengths of corresponding special segments within the similar triangles. So we're talking about altitudes, medians, angle bisectors, and so forth. So once again, the altitudes, and definition of an altitude is a line dropped from a vertex perpendicular to another side of the triangle. So the altitudes extending to corresponding sides of similar triangles are in the same ratio as the lengths of the corresponding sides. Here's what that would look like. We have triangle ABC and triangle DEF. They are similar. Now we can prove that they're similar by proving that at least two sides are similar, or that a side angle side is similar. But let's go ahead and start off by setting up a proportion, and we'll use EY, the altitude of the smaller triangle, to BX, the altitude of the larger triangle, and then we'll use 3 meters, which is the long leg to the right on the triangle, to 6 meters, which is the long leg to the right on the right side of the left triangle. If EY over 4 meters, which is the altitude of BX, equals 3 meters over 6 meters, we can take this 3 and 6 meters and we can reduce it. Meters cancels out meters. 3/6 is 1/2. So EY over 4 meters equals 1/2. Now if we multiply across, we have 2 EY equals 1 times 4 meters, which is 4 meters. And we need to solve for EY, EY being the altitude of the smaller triangle. And we do that by dividing by 2 on both sides, and EY equals 2 meters. So we've taken the proportion, and you can see that this 3 to 6 is 1/2. So we're going to make the altitudes also be in that same ratio, and we can do that because we know these triangles are similar. So if EY is 2 meters, if we replace EY right here, it's 2 meters divided by 4 meters, which is 1/2, and that does prove itself out. Now we have another 11.5.1, but this is B. Instead of altitudes, we're going to talk about the lengths of the medians extending to corresponding sides of similar triangles are in the same ratio as the lengths of corresponding sides. So a median, if you remember, is a line dropped from a vertex that will cut the other side in half, or bisect the other side that you're intersecting. So what we have here now, we have an example that asks us to find AD, which is one of the medians, given that these two triangles are similar. So I'm going to place AD on top on the left because that's what I'm solving for. And I'm going to compare AD, the median in the larger triangle, to XW, the median in the smaller triangle. And then I'll take the side AC that has a value. And if we were to flip this triangle, we'd see that AC is corresponding to XZ, and there we have our proportion set up. Now AD will be over 6, and 12 will be over 8. There's the lengths of 12 and 8 right there. And if we go ahead and reduce 12/8, that becomes 3 seconds. And if we multiply across, we have 2 AD times 6 times 3, which is 18. And 2 AD, or 2 can divide both sides, and you'll end up with AD equals 9 feet. I wanted to show you right here how the book does it. I find this to be very confusing, but they actually don't even show the 2 times AD. They just say that AD equals 6 times 3 seconds. That can be a problem, so I don't do it that way. Alright, another theorem in that series, this is 11.5.1c. The lengths of the angle bisectors extending to corresponding sides of similar triangles are in the same ratio as the lengths of corresponding sides. So once again, 2 triangles that are similar, and you can see that they have these angle bisectors. KM is the angle bisector of the smaller triangle. TV is the angle bisector of the larger triangle. And what we're going to do is go ahead and compare the angle bisectors. We have KM divided by TV, and we'll use one of the sides, and we'll set it to KL is divided by TU, the same side. Now, I don't have values for this, so this is as far as we're going to go on this pair of triangles. The last theorem will be theorem 11.5.2. Now that we've shown that all the parts of triangles can be proved similar using the same ratio that the 2 triangles have, you can also use those ratios to solve for perimeters or area or volume. So we have triangle ABC, and it's similar to DEF. The theorem tells us the perimeters of similar triangles are in the same ratio as the lengths of the corresponding sides. So the ratio for this would be the perimeter of triangle ABC divided by the perimeter of triangle DEF will equal this side length here, x, over the corresponding side length, y. Now, if you had numerical values here, you could plug those into x and y. Or if you had one of the perimeters, you could put that into the proportion, and you would be able to solve. So you still do it the same way, it's just that you'll have a perimeter instead of a side length. Let's look at a couple of examples. We're going to solve for AB, this side to the left of this large triangle, if triangle ABC is similar to triangle GEF. So I'm going to take what is the altitude. I can tell it's an altitude because it intersects this base at a 90-degree angle. And I'll put the altitude of the larger triangle over the altitude of the smaller triangle. We have 4/3 equals, I'll go larger triangle, x plus 1 to x minus 1. We will multiply across, and we have 4 times x minus 1 equals 3 times x plus 1. And if we go ahead and use distributive property, we have 4x minus 4 equals 3x plus 3. I'm going to add 4 to both sides and subtract 3x from both sides, and our answer will be x equals 7. So then to solve for AB, if x equals 7, x plus 1 would equal 8. A second example, we're going to solve for RT. That is the length right here in this large triangle. If triangle MOP and triangle RAG are similar. So we have medians. They're dividing, they're being dropped from the vertex here. And we're going to go ahead and set the medians in proportion to each other and 2 of the side lengths to each other. So I'm going to take the portion we're solving for, RT, and start with that. And RT I will place in proportion to the median of this triangle, which will be 10. And then that will be equal to MK, which corresponds to RT, over 8, which corresponds to the length of 10. And now we multiply across. We have 8 RT equals 10 squared, which is 100. And if we divide by 8 on both sides, RT equals 12.5. And the last example. Find OD if triangle TOP is similar to triangle BAG. Now this one is about angle bisectors, so that was the 11.1 C. And it's a little difficult to see these. I would redraw them and put O up on the top and A up on the top, and A will actually have to be flipped. But comparing them, we have OP, this side length, and sorry about that, I just caught an error. We have OD, which is the angle bisector, in proportion to 12, the side length of OP, and we have that equal to the angle bisector of the smaller triangle, which is 6 over the side length of 9. If we multiply across, we have 9 OD equals 72. Divide both sides by 9, and OD equals 8. So there you have it. Your homework is numbers 1 through 6. If you have any questions, be sure to contact me.